Here's the molecular orbital diagram for the dihelium molecule. Now, helium has one more electron than hydrogen. So while hydrogen was a 1s1, helium is a 1s2. So initially, if you will, you'd have like two up arrows, one up, one down, in each of the heliums. So there's 4 electrons total. And those 4 electrons, the first 2 go in the lower helium bonding orbital, but there's also now some electrons for the anti-bonding sigma star 1s. So they'll end up being 2 1s electrons in the sigma bonding and 2 1s electrons in the sigma star anti-bonding. And the question at this point is, do you think that this is going to form or not? And you can probably guess what it is, but let's formalize it. Bond order is a way to tell if the molecule is going to form or not. And bond order is related to, but not the same as, the bond order we looked at in the last chapter. In the last chapter, we looked at the Lewis structure, so a single bond was bond order 1, a double bond order 2, etc., etc. This bond order is similar, but it's a different definition. When it comes to molecular orbitals, bond order equals 1/2 times the number of bonding electrons minus the number of anti-bonding electrons. If the calculated bond order is greater than 0, that means you have a stable molecule. It's a molecule that can form. On the other hand, if you have a bond order equals to 0, and we're going to see some of those, or in other classes, you actually might have a bond order less than 0, but we won't see them in this class, those molecules are unstable and they probably won't form. So let's apply bond order to the 2 molecular orbital diagrams we've seen so far. Here's the H2 molecular orbital, and again it shows 2 electrons in the bonding sigma 1s, but no electrons in the sigma star 1s. Hydrogen doesn't have as many electrons as helium. So for this molecule, 1/2 parentheses bonding minus anti-bonding electrons, 1/2 parentheses 2 minus 0, bond order 1. So if the bond order is greater than 0, we'd say it's stable. You bet, hydrogen is a stable molecule. It's something that will exist. Now, it doesn't mean it's not reactive, all that kind of jazz, but it does mean it's something you can put in a jar, if you will, and show your friends. Although hydrogen doesn't really have a color, I digress. It's something that's stable. Hopefully you get the idea. Notice that in this context, the bond order works out pretty well when it comes to the Lewis structure. The Lewis structure for H2 would be like this, all right? 1 electron on each hydrogen, making 1 sigma bond. The hydrogen only needs 1 bond, so it's happy. The single bond between the 2 hydrogens would also be bond order of 1, just like the molecular orbital diagram, which again is this part here in the middle, just like the molecular diagram also had a bond order of 1. So often MO and Lewis structure's valence bond will be very similar. Not all the time, but a lot of the time, most of the time, I would argue they will be stable. Let's look at another example. We looked at dihelium earlier. Dihelium has this structure right here, where now both the bonding and the anti-bonding orbitals have 2 electrons inside them. Well, for dihelium bond order, 1/2 parentheses bonding 2 minus anti-bonding 2, 1/2 2 times minus 2 is 0. So dihelium is unstable. Dihelium, to the best of my knowledge, has never been found. There's no energy reason for the dihelium molecule to come together. Each individual helium atom is really stable by itself. There's no reason to form He2. In hydrogen's case, you had a high energy savings making the H2 molecule, so that's why H2 is happening. Bond order was equal to 1. Dihelium, though, each helium is so stable it doesn't need to react, so we would not predict the dihelium molecule to exist. It has a bond order of 0.